Drones are an everyday sight, whether a hobbyist in a park or a delivery flight. We're accustomed to the hum as one darts past. Because they are so common, it's easy to overlook their aerial agility. They move with a precision that suggests a highly complex internal mechanism. Yet the simplicity of their construction hides a sophisticated engineering puzzle. Traditional aircraft rely on moving parts to change direction. Airplanes use adjustable flaps and ailerons, while helicopters require a tail rotor. A quadcopter lacks these control surfaces. Its rigid frame consists of 4 fixed motors that cannot tilt or move independently. This raises a problem of basic geometry. A machine with no moving parts to direct airflow must still find a way to navigate 3-dimensional space. Solving this requires a departure from traditional mechanical steering, relying instead on the precise manipulation of physical laws. Consider the basic challenge of a stable hover. If all 4 rotors spin in the same direction, the force of the air would push back against the blades, causing the drone's body to spin uncontrollably in the opposite direction. This top-down view shows rotation managed. 2 motors spin clockwise, 2 counterclockwise. Their opposite rotational forces cancel out, bringing total anchored momentum to 0, keeping the chassis stationary. With rotation balanced, it maintains altitude by ensuring all 4 motors push down with equal thrust. A steady hover is a stalemate of balanced forces, requiring constant, active adjustment from every motor. Moving forward or sideways presents a second puzzle. The engines are bolted in place, pointing straight down, yet the drone must generate horizontal momentum. The solution is a deliberate tilt. The drone decreases thrust in the front 2 motors, while simultaneously increasing thrust in the back 2. This imbalance forces the drone to lean. A portion of that downward thrust is now directed backward, pushing the drone forward. This same logic of creating thrust imbalances allows the drone to accelerate backward or roll to either side. Directional flight is achieved by sacrificing equilibrium to create a state of controlled falling. Turning the drone's nose, known as yaw, is perhaps the most difficult maneuver to perform without a rudder or tail rotor. This pivot relies on the conservation of angular momentum and the drag torque acting on the propellers. To turn clockwise, the system decreases speed in the 2 clockwise spinning motors. To maintain 0 angular momentum, the rigid drone body must rotate clockwise to compensate. Because slowing 2 motors causes altitude loss, the counterclockwise motors simultaneously speed up to maintain necessary upward thrust. Turning is the result of using the laws of rotational physics against the drone's own mass. When a drone performs a rapid, sweeping turn, it is managing all of these complex physical adjustments simultaneously. Each movement is a sequence of high-speed calculations, balancing vertical lift against horizontal momentum and rotational torque. Since there are no mechanical links to steer the craft, an onboard computer must translate a pilot's joystick movements into thousands of individual motor speed adjustments per second. This design creates an interesting technological trade-off, a mechanically simple frame that requires immense computational power to fly. The quadcopter's design effectively replaced heavy, complex steering hardware with the application of computational physics.